everyone. In this session, we will talk about descriptive and inferential statistics. The learning objectives for this lecture are to understand the purpose and importance of descriptive statistics, to review the concept of histograms, box and whisker plots, and the most common measurements of location and dispersion. We also want to explain the purpose of inferential statistics and point estimates for a population parameter, and to identify unbiased point estimates for the mean and standard deviation of a normally distributed random variable. The term descriptive statistics refers to using empirical methods to describe populations. And this means taking data from a population and arranging and summarizing it in order to obtain useful information. Descriptive statistics do not, however, allow us to make conclusions beyond the data we have analyzed or to reach conclusions regarding any hypotheses we might have made. They are simply a way to describe our data. Now, entire textbooks are dedicated to this area of statistics, but for our course, we will look at histograms and box and whisker plots for displaying data in a useful way, and we will review commonly used parameters for measuring location and dispersion of a population. And here in this lecture, we have a few examples in order to illustrate these tools of descriptive statistics. So, first, the frequency distribution. This is the tool used to describe the variability in a population. It shows how the units in a population are distributed within the possible range of the values. A frequency distribution can be drawn for an entire population by taking a measurement on each unit of the population, although this normally will take too much time and resources to do. So frequency distributions are usually made from data obtained only from a sample of the population, and this frequency distribution then is called a histogram. Now here's our example. Here we have the fill weights of cans of deodorant taken from a sample of 100 cans. This data here is in grams. So to construct the histogram, we look first for the minimum and maximum values, which are here 175 and 346. So the difference in these, though, the difference of the max minus the min is called the range. And so we have 346 minus 175, get 171. This is the range grams, the range of our data. We then divide this range into a convenient number of intervals. Those are also called bins. We want to tally the observations for all 100 measurements here into our different bins. And the tally will give us the frequency distribution of the data in the number of values falling into each bin. We then will calculate the percentage frequency distribution by calculating the percentage of the data falling in each bin out of the total number of values in the sample. And here we have the resulting diagram. So we have a range that encompasses from 160 to 360. Our bin length is 20 grams for each bin. And then we have performed a tally to count the number of values that fall within each bin and divided each by 100 to get the percentage frequency distribution. Now, looking at this data, we can learn quite a bit about our population by studying the histogram. The histogram can give us an idea as to where on the x-axis, which central point the population is distributed. So here we would say roughly around 270. It gives us an idea of the variation of the data. And if we had values such as a upper and lower specification limit, we could answer questions such as, are all the measurements in the population falling within specifications? Or is the variability within an acceptable level? And furthermore, The histogram can point to directions for solving any problems that may exist or for moving forward in a quality improvement program. And so here we have another example. Here we have a manufacturer of thermostats using toasters and ovens was expecting considerable returns from customers because of thermostats failing in calibration tests. So thermostats used in toasters and ovens. Now, how many of you have had experience with thermostat manufacturing? And here we already have a key lesson in quality management. You, as a quality engineer or quality manager, need to understand the need for bringing together a team for solving quality problems. You can still work with the information you have or you get from the team to help guide the quality improvement program. So let's see what our team gives us. The failures were traced to a width of a small keyway on a tiny shaft on the thermostat. So I don't know what this looks like. I've never worked with a thermostat before, but I have a small shaft which has a width, a small keyway here. This is called a dog width. And we understand from our extras that the failures were traced to this width of the dog width. We also learned that these keyways were typically cut on a milling machine. And this milling machine had 2 cutting heads. And then they were collected in a common hopper below the 2 cutters. We also learned that the uniformity of the dog widths has to be ensured in order to prevent calibration failures. So now going back to our last lecture, we have very little information here, but we can already construct a simple process flow. So input would be the shaft, or the uncut, we should call it, the uncut shaft, into a milling machine, which we know has 2 cutting heads, comes out and goes into a storage hopper, and then moves on to the next stage. Now, to solve this problem, a sample of 100 shafts, so n equals 100, was taken from the hopper of one of the milling machines. And the widths were measured and plotted on a histogram. So here's our histogram. What do we see? First of all, we have the keyway width, the dog width here. We see a variation from 0.24 to 0.29 inches. This is our random variable. We have the frequency of the widths contained. We've developed bins of a certain small width, and the frequency of each width occurring within a certain bin is plotted here on the y-axis. Now, this is not a model. This is the empirical measured data from our experiment of 100 shafts. The upper, lower, and lower specification limits are also specified here. And we can see that already at least half of our key widths are out of specification. They're above the upper spec limit. Now, can you see anything else in this graph? Can you already see what might be the problem based on the information we had from our expert team? If I draw this in here, what we can see without doing any special analysis from our histogram is that our histogram typifies a bimodal distribution, which is a frequency distribution with 2 modes or 2 different peaks in the data. And this indicates that there are 2 different distributions mixed together in this population, one which is within the specification and one which is almost outside. Now, from this information, we could guess that the difference in the 2 distributions might have been caused by the difference in the way that the two cutting heads in the milling machine were cutting the keyways. Now, referring to our last lecture, we would then construct a sampling plan. We know what we want to measure the key widths, and here we would plan to do a stratified sampling where we would select products from both of the different cutting heads because we suspect that there's a difference there. And in fact, 50 shafts were taken separately from each of the two cutting heads. Separate histograms were drawn, and it was easy to see that one of those cutters was producing keyways within the specifications, and the other was producing keyways which were not within the specifications. And once that's clear from the data, then the technician can go and find out what is the difference. And in this case, the difference was found, the faulty cutter was adjusted, and after the adjustment, there were no more thermostat calibration fails at the customer. Okay, so another graph of data that provides very useful information in addition to our histogram is the cumulative frequency distribution. So here again we look at our histogram. Now this we're back to our fill weights example. This is the deodorant fill weights in grams, 100 fill weights, and remember we saw that data was centered around 270 grams. We can look again at this information and this time plot it as the cumulative frequency distribution. So we have the same fill weight data on the x-axis, but here we have instead of the frequency distribution for each individual bin, we accumulate this from smallest to largest. So what does this tell us? Well, for example, if we look here we're at about 40%. What this means is that about 40% of our fill weights in the sample that we have are less than or equal to 260 grams. And of course it makes sense that from all of our data, we have 100% of our data is less than or equal to 360 grams. Cumulative density function then gives us information on what percentage of our data are below certain values, from 0% up to 100%. And this brings us, of course, to the idea of percentiles, or 2 percentiles. We're here 50%. It's our 50th percentile here. This is our 100th percentile. And leads us then to box and whisker plots. These B&W plots are another very compact way of representing a population with variability. And this is one of my favorites, the box and whisker plots. I put a star by that. It's a graph showing several percentiles of a given set of data. So it shows the minimum value, which our text calls x0, and the maximum value, x100. It gives the median, which is the x50, which means that 50% of our data are less than or equal to x50, and 50% of our data are greater than or equal to x50. It also gives us the first quartile and the third quartile, and these are the points at which 25% of our data is less than or equal to x25, and 75% of our data is less than or equal to x75. Now, we're not going to be asked to construct these in our course, but I do want you to understand why they're useful and what data points they contain. So, to construct the box and whisker plot, first you construct the box using the third and first quartile. Then you draw the whiskers out to the minimum and the maximum values, and you draw a line for the median. We have one example to show how this is useful. We have here temperature data taken from an iron foundry, which makes large castings. So you have very, very hot molten iron that is taken from a cupola and then transferred over to be poured into the molds for the castings. Now the top graph is a histogram of the tap-out temperature. So you can see this ranges from a high value 2,537 degrees Fahrenheit to 2,597 degrees Fahrenheit. Then the molten metal is transported over to where it is poured, and we have the pouring temperature here. And here we have some specification limits. Now, it's very possible for you to compare these two graphs, just looking at the data like this. You can see the minimum and maximum values are a little bit different, so you can't quite compare them. But you can certainly use the histograms to look at the two data plots to draw some conclusions. But what is more useful is the box and whisker plot. And here we have the box and whisker plot of the tap-out temperature and here of the pouring temperature. And here it's very clear to see the median values here show a difference of about 10 degrees Fahrenheit. So the pouring temperature is about 10 degrees lower than the tap-out temperature from our data that we see. We see that the overall spread of the data, minimum to maximum, is about the same for both. And indeed, the interquartile spread, the spread between the third and first quartile, also about the same. Now we can also see maybe more easily here that the median for the pouring temperature, it's roughly in the middle of our distribution. We have this little outlier here, but very low. Whereas here, the median, there's a fatter tail on the side. So the median then is lying closer to one of the ends of the distribution. So hopefully this gives you then an idea of how effective a box and whisker plot, because we have these in some of our examples. So just to close this, the other important tools of descriptive statistics are the calculated parameters to measure location and dispersion. The important measures of location are the average, the median, and the mode, where of course the average is the center point of the distribution around which the data is distributed. The median is the 50th percentile, or x50, as we just looked at, and the mode is the value that occurs in the data with the most frequency. So to measure dispersion, we've already talked about standard deviation. This is the variability about the center point, about the average. The range is the difference in the largest and the smallest value. So these we've definitely seen before, and we'll of course use them again. This completes then the descriptive statistics that we'll be using in this course. By taking data from a population, we can calculate characteristics of that population using the data available, and we can arrange and display the data in order to obtain useful information. So now we will move on to inferential statistics, where we will use the measured data to infer characteristics about the population and draw conclusions based on sample measurements.